Hello and welcome to this video on SUVAT equations. SUVAT equations are an abbreviation. What they stand for, or what they mean, are equations of motion for linear constant acceleration. So what this means is these equations are useful for calculating the motion of anything that travels in a straight line and accelerates or decelerates at a constant rate. So what SUVAT is abbreviated from is these terms that make up the equations. S stands for distance, U is initial velocity, V is final velocity of the system, A is for acceleration, and T is for time. So when you're calculating in a system, you need to know three of these, three known to calculate one answer, and then one doesn't really matter. So you can have three, as long as you know the values of three of these, you can calculate any of the other two, and the other one can just be ignored. So now I'm going to go through the five SUVAT equations, but two of them are very similar. So the first one we'll start off with is S equals U plus V over 2 times T. This equation, this part here, gives you the average speed, or the average velocity, over the time, and this is the time. So when you have velocity times by time, you get distance, which is what this equation is. We'll name this equation 1 over here. Equation 2 is going to be V equals U plus AT. This equation, you have the initial velocity times by the change in velocity. So the acceleration times by the time gives you the change in velocity. So the initial velocity plus the change in velocity gives you the final velocity, which is the explanation for that equation. The next equation is S equals UT plus half AT squared. So the best way to explain this equation is to draw a graph. So if I have on the y-axis, if I have velocity, so write vel, and on this one I have time. So imagine you have a system which starts off here, say that's U, and ends up at V. So we can draw that there. So that's the system. It starts at time equals 0, it starts off at U as initial velocity, and at time equals T, ends up at the final velocity. To calculate the distance that it's gone, you need to know the area under this graph, the area under here. So to do that, we can split this up into two parts. The bottom part is very simple, that's U times T. But for the top part, first we need to know the height. The height is the change in velocity, which we noticed earlier from up here, is AT. So the area of this is half AT squared, we're timesing it by obviously the bottom bit here. So we know that the total area is UT plus half AT squared, and the area is the distance. That's the explanation of this equation. Similarly to this one, we have S equals VT minus half AT squared. This is exactly the same as this equation, but you are taking this part, the whole of it, and minusing that, or minusing one of these two triangles, and it gives you the same answer, using the same principles, but you minus it instead. And for our last equation, well, these ones are really 3 and 4, but they're very similar. And our last equation is the most complex. V squared equals U squared plus 2AS. Move that up a little bit. This equation is quite difficult to derive just logically, as have done with this previous ones. How can we derive mathematically? So first of all, let's have v equals u plus at, and rearrange that to be t equals v minus u over 2. Over a. Over a. That's just that equation rearranged. And now, if we substitute that into 1, so if you bring 1 down here, and substitute that value, that t there, with that, we get s equals u plus v over 2 times v minus u over a. And then rearranging them, you get, just with a bit of rearranging, timesing things through, you get v squared equals u squared plus 2as. It's not particularly important to know how these equations are derived themselves, but it's useful to know a little bit of the theory behind them, as I've done. So, if you notice with all of these equations, what they give you is, I said, the ability I said earlier, to work out one answer knowing any 3 of the others, because each of these only has 4 or so values in. And basically they all work out, that means you can work out anything from them, which is quite useful. So now I'm going to do an example. Now for this example, I'm going to try and make it as realistic as possible, so you can understand sort of why these equations are useful. So the question is going to be, imagine if I throw a ball up in the air from where I am now, with a velocity of 5 meters per second. How high is it going to get above the point that I let go of the ball? At what point is it going to stop going up any further? So the first step for all of SUVAT equations is always write SUVAT down. Write it down so then you can think it through logically. So the distance, well, that's what we're trying to find. So I put a little question mark here. The initial velocity is how much I'm throwing it up with. So that's 5. We want to know the distance when velocity is 0, so when it stops going up anymore. So final velocity, 0. Acceleration, now this is going to be minus 9.81. This is because this is the value for acceleration on Earth. If you drop an item and ignore stuff like air resistance, it'll accelerate downwards at 9.81 meters per second. So this is a constant that you will have, nor might be given to you in an exam if you need it. But it means this scenario can be a real life example. And time, then you can ignore that. So here we have 3 known values and what we need to calculate, which is brilliant. So for this one, we need to use the equation 4. You need to use this equation here, because when you look at all the equations, we don't have t, so we've got to look through. That one has t, that one has t, and that one has t. This is the only one that doesn't have t. So for this is one we need to use. For each question, write down this, see which numbers you have and which ones you need to calculate, and then just look through the equations to see which is most appropriate. So, v squared equals u squared plus 2as. Now, we need to rearrange this to get s on its own. So I'll quickly do that. V squared minus u squared divided by 2a. So therefore, this is 0 squared minus 5 squared over 2 times minus 9.81. Now this goes to minus 25 over minus. So 2 times 9.81 is 19.562. Sorry, minus 19.62 equals s. So minus 25 divided by minus 19.62, 0.62 gives us 1.274. So that means if you throw a ball up from your hand at 5 meters per second, the maximum height it will reach above your hand is 1.274 meters. So this is how SUVAT can be used in real life examples, and there are many, many more examples. As said, these will work for any situation with linear constant acceleration to give you real life useful answers. Thank you for listening. I Hope you find this video useful. Subscribe if you did. Thank you.